Greetings, everyone. Welcome to KLIPPEL Live, a series of webinars focusing on acoustical measurement of sound system equipment according to IEC 60268-21. I hope June finds everyone well as we continue to recover from our worldwide pandemic and that things are recovering in your offices and lab spaces. My name is Kent Peterson and I'm coming to you from Warquin in Minneapolis and St. Paul. This week, restaurants and entertainment venues are beginning to open. They're beginning to open their doors a little bit to small amounts of people. And while the home audio, headphone, and smart speaker industries seem to have kept a pretty steady business during this time, please keep your pro audio and studio sound brothers and sisters in your thoughts as the live music industry is going through some very tough times. Support your local music scene as you are safe and able. As a studio owner and live musician, I've finally gotten a haircut in anticipation of getting out there. It was getting pretty thick and ugly. It gave me a nice trim, but unfortunately they were not able to add more hair where I need it, despite me asking numerous times. Okay, thanks again to all of you who have been attending these webinars regularly. It is nice to see all of your returning names, and I hope you enjoy today's installment entitled Best Practices for Harmonic Distortion Measurements. We'll again have some polling, and also remember to post your questions in the Q&A button below. And if you have any comments of an emergency nature, such as all of the audio or if there are video problems, please let us know in the chat window. If it's something we're doing, we'll try to fix it. During the course of the presentation and immediately afterwards, we will address your comments and questions, so keep them coming. Without further ado, please let me introduce Dr. KLIPPEL to start our presentation. Good morning, or I should say good afternoon, Wolfgang. I hope you are well, and please assume control.
Yeah, thanks, Kent. Let's use the time. We have today a lot of interesting information. I hope I can use the time very well. Before I'm starting, as usually, I do a first overview on the previous session. In the first 5 sessions, we have spoken how to generate more or less standard conditioning here in my office. And now we are in the second session, starting with number 6 up to 10, where we are speaking about distortion measurements. In the last session, we have spoken, so that is here the beginning, the first, here with a laser scanner and so on, and getting comprehensive 3D information and how to calibrate here the measurement position as if we would have perfect anechoic condition and far field condition. And finally, we are now here with the distortion measurements. The last time we measured the amplitude compression, now we are coming to the harmonics. The measurement of the harmonic distortion is very important. It is not new, but the standard provides a lot of interesting new ideas. You will see. So what is our topic today? An overview on the new methods. That's the most important things. We are discussing difficult problems which are related to the harmonic distortion. How should we present them in the best way? Absolutely or relative, in percent or in dB, and so on. And what is our goal? Our goal is to simplify the interpretation of the results, to get more meaningful information out of the measurement. That's our goal. And I will illustrate that with some practical measurements here. Again, we have a lot of polls, and so it is a good time. I hope so. Yeah, harmonic distortion is just a symptom, but we are using a very special signal. We are using a sinusoidal tone. Actually, one frequency only is excited at one time, but we get much more out of the speaker. We see the fundamental, but we see harmonics, we see sometimes subharmonics, and we see noise. Here it is illustrated. That's more or less the frequency axis. That's a spectrum generated by one frequency that corresponds with the input signal. And then we see here some subharmonics at half of the frequency or 1/3. And the same is here for the harmonics. There are multiple of the excitation frequencies. So we have spoken about that. Now we are on the single tone, a very simple, maybe the most simple signal or stimulus we can apply. And we are applying a spectral analysis, an FFT, or we can use a high-pass filter or band-pass filter, and then we see a spectrum. So what are the benefits of this measurement technique? It's simple to generate. We find a sinusoidal generator in any workshop. It reveals the harmonics, sometimes a DC component. We can nicely access the maximum output of the fundamental. We have spoken about the compression last time. We can also make the measurement a little bit faster, and we will speak about that, how to do a sweep or a chirp, yeah. And that's why the chirp measurement with the sinusoidal tone is very important for rub and bus testing. But we will come back to that in section 9. Oh, actually 10. That's not correct here. Yeah, what are the drawbacks? We see no intermodulation distortion. We have only one tone today. And actually, it is not a comprehensive testing to see all the possible effects and symptoms generated by the nonlinearities. That should be clear. But it's still a very, very important measurement. Now we are coming to the first poll. Which stimulus do you use for the measurement of the harmonic distortion? So we have only one frequency, but we can apply the single frequency for a long time, that we get getting steady state condition, so that we call it single tone measurement. Or B, we have a stepped sine sequence of switched tones. So we have at a certain point a transient, and we ignore that, and we are waiting again, usually, that we get steady state condition. Finally comes the sinusoidal burst. That is more or less a tone with a shaping. So, and then it's a long break usually. Then we can use a continuous sinusoidal chirp and other signals. So now I see the result. I see the winner is 100% the chirp. That's a modern signal. And actually the IEC standard defines very clearly what kind of properties we find in the chirp, how to specify that, and something like so. So that's the way to go. It is the best signal to measure in a very short time and to get a lot of meaningful information. And thanks to Professor Farina, we have also a very nice idea. By the way, John van der Kooi had a similar idea before that. So we have a very nice idea to measure the harmonics with this chirp in a very quick way. So then there are other interesting things. Then are coming the stepped sine. He is still fine. With 40%. Why? We have some unique, interesting properties in the stepped sine. I'm coming back to that. So that's 100% what I expected and what is 100% correct. Yeah, and then comes the single tone. So we have 100% steady state condition, and then only 13% is a burst. Actually, I intended to show something with burst measurement, but it's maybe too much. It's the very end of my presentation. I have to kill that, but it's good that it's listed here. Then other 3%, I don't know what that is, but maybe you can use here the chat window and tell me what you mean. Okay, let's go on. How to measure harmonic distortion. Here you see the three most important things. That's the stepped sine, the sinusoidal burst, and the continuous chirp. First is the principle of distortion separation. And you see we are using usually an FFT or Fourier transform to come to the spectrum. But with a chirp, we can also use, in some case, a tracking filter, or we can apply also some windowing. We have spoken about that, not only to the fundamental impulse response, but also to the harmonics. I will speak about that. So that's a very nice feature, very important. Yeah. Okay. Continuous excitation? No. Here we have to switch, or there's a decay of the signal in the burst. But with a continuous chirp, we are going over the full audio band without generating a click. That's very important for rub and bass measurement. So we have a very nice continuous excitation. Very good. Okay, then we have steady state conditions. In the step sign, we can realize that, but not here in the other two things. The measurement time, the total measurement time is not very good here in the step sign and with the burst. Usually it takes minutes. But with a continuous chirp, we can measure a speaker in end-of-line testing in less than half a second. That's possible. It's very, very powerful. Yeah, and here you see different modules. I'm coming back to them, which are provided by the KLIPPEL analyzer. I will not speak, I have not the time, speaking about the QC end-of-line testing, which is quite fast, but this is a different topic. Okay, let's go on. Sweep speed of the chirp. Now let's speak a little bit about the chirp. There are different ways to change the frequency. Here, the first one is a linear chirp, but it is plotted here over a logarithmic frequency axis. That's why this line is here distorted. If this would be a linear frequency axis, then it would be a straight line. But if you are listening to that, oh, that's a little bit too loud, sorry. You have to bear that. I will not use the time for, I say hello, then you can move your headset away the next time if the next signal is coming. It's a bad signal for testing. It doesn't fit into our logarithmic world, audio world, so don't use that. There are some guys who think it's valuable. I don't see the point. So the next signal, which is quite popular, is a logarithmic chirp. Here on this logarithmic frequency axis, we have a linear mapping. Sorry, now comes the signal. Remove your headset. So, okay, you know that very well, I think. And then we have another thing that's maybe a chirp with increasing sweep speed. Something like that here. That's the opposite thing. I don't know whether it comes. Be safe, take your headphone again. Yeah, okay, that's a different story. All of them are existing and are used in some measurement equipment. KLIPPEL is using that here very much, and we like it very much. And now comes the next poll. Which sweep speed profile do you use? First, we have A, here's a linear mapping, logarithmic time frequency mapping. Then comes here the thing with the increasing sweep speed, and then any other. Okay, we have already a result. I expected that. Almost everybody is using the logarithmic time frequency mapping. It has some huge benefits, and you will see see them very soon and how we are using them. So in the other, that's one person. It might be interesting if you are telling us what you are using. Okay, now let's speak a little bit about the logarithmic one, because that was 80% more than that. Here you see that's the amplitude. Here that's our amplitude, fixed amplitude. No, it's not fixed. It might be frequency depending to generate an amplitude shaping. And then we have here the interesting term. The frequency is changing with time, but the frequency mapping was that here. Sorry. Yeah. Here you see the mathematical equation from that. Yeah. So we have a constant logarithmic sweep speed. That's more or less this term here on the exponent, weighting more or less the time t. So from that, we can immediately calculate the group delay. What means that we have at a certain time, a certain frequency over the scan. So that corresponds with the time delay. No? So That's quite simple, but we can, especially with this amplitude shaping, we can shape the amplitude spectrum as we like that. We can plot this here with a relative bandwidth, and it looks like pink noise, or on an absolute scale, something like that here. Okay, that's quite nice. So it simulates, if you like, a dense audio signal, but keep in mind at a certain time we have only one frequency. Okay, we have some very nice properties of the logarithmic chirp. Here you see the frequency or the time frequency analysis, such a spectrum. That's the time axis here, time. That's about 1.3 seconds. And here we have almost 3 decades of frequencies. That's here 100 Hertz, 1 kilohertz, 10 kilohertz. Yeah. And here the color is more or less the amplitude. So in this analyzed with wavelets, so we have a very good resolution at high frequencies. And now the first thing, that's here our fundamental. We see here again our logarithmic frequency axis, our time, the linear mapping. And then we see here at a later time coming the sound reflections from the walls, from the ceiling, so it arrives later. And we have here some harmonics. This is here the second, and that here is the third. Yeah, and now let's assume at a certain time, our generator produces a certain fundamental frequency. That's here actually 500 Hertz. Yeah. Then the device, the transducer, the speaker, generates some harmonics. Let's take here the second harmonic, which is actually at 1 kilohertz. Yeah, and so that means our speaker synthesizes a new frequency which has not been generated by our generator. So actually the 1 kilohertz tone arrives a little bit too early. Yeah, it will be actually transmitted by our generator 160 milliseconds later. So we have actually an acausal behavior of our speaker. He sends a signal which have been not generated by our generator. So that comes because we are generating harmonics. So the third harmonics will be at a higher frequency, so it will arrive even earlier than that. What means that? If we are playing our chirp twice, usually we have to do it because this speaker, especially here the JBL Bluetooth speaker, has a time delay, a latency of 20 milliseconds. So usually we miss a little bit the end here. Here you see a small dip in that. That's already part of a new chirp. I glued them here together, so my gluing was not perfect. So that's the first chirp. That's the second one. And here you see the impulse response. Yeah, that's the first impulse response, and here's the second. And that's the energy time curve. That's more or less that here. We are taking the absolute value and taking the logarithmic value from that, so we can look down here almost 80 dB. Yeah, that's a lot. And what do you see is here more or less the energy from the impulse. It's close to 0. Here is the same information. And then we have the decay from the room reflections, then comes noise. And then you see again some peaks in that. And that are the acausal responses from our nonlinearities. And that are exactly the 160 milliseconds delay coming from our second order distortion, and then the third, fourth, fifth, sixth, eighth, and so on. So actually they're coming earlier than the fundamental. That means acausal. No? And Farina had this beautiful idea to cut out with windowing those impulse responses from the harmonics and calculate more or less the harmonic distortion from that. Very convenient, very clever, very nice. No. Okay. If you would like to learn more about that, there's a very good paper from Farina. Please get it and read that. Okay. Yeah, now it's time for a demo. I'm using here our TRF module for that. using here a chirp. Yeah, and I'm switching immediately over here to the software. Okay. We are now here in part 8, measurement of harmonics. I close that here. We are here now with the first experiments measuring harmonics with the TRF. And we are starting here with the first measurement. I did it already, but I can redo that. I'm starting here the measurement. Oh, the Bluetooth device is switched off. Now it's switched on. You see it's only noise. Maybe I have some time to show you what the TRF is doing. Maybe I have to switch on here again, here my lenses. We are starting at 70 Hertz. We end up at 20 kilohertz. So we end up with a frequency resolution of less than 1 Hertz, and the length is 1.4 seconds. And we are doing here the measurement at the maximum Umax for this Bluetooth device. This is more or less the maximum input for the pink noise signal or the typical program material generating SPL max. So now it's time to start that. Again, we have here usually 2 sweeps, and then we get here our results. Okay, I can clear that a little bit. That makes sense. Okay, I remove that. So this is our impulse response. I make it large, and if I zoom into that, then you see at the very end here coming up more or less the impulse responses from the second harmonic, from the third. Yeah, that's more or less that. I'm undo that, then you see here the impulse response, and that corresponds with those spikes here. But if you look to the results, that's our magnitude response without room compensation filter, correction filter. So we have here a distance. Please, Andrew, switch on here the camera of 30 centimeters. So we see some room reflection, and that generates here actually this bad behavior. Okay, but if you are thinking about harmonics, please look here to the fundamental response. This is more or less, that's not the magnitude response. That's if you apply the voltage at the input of the device and you measure the SPL with the SPL meter, then you see here the SPL level. That's here the total fundamental. Then we have here the THD, and which is almost identical with the second order distortion. You see second order are important here, are dominant, but the third order distortions are much lower. They are only important here at higher frequencies. So that's the result what we get from the absolute, here in the absolute presentation. So that's not in percent, that's really in SPL, so really in normal SPL level. Then you can immediately compare that with the fundamental. Here you see we are 20 dB down with the THD, and with the second we are almost 30 to 40 dB down. Yeah. If you are calculating the relative distortion, then it looks a little bit different. Then you see it looks something like that. I'm speaking very soon about that. We are dividing more or less the distortion, the THD level, here's this one, by the fundamental. And now you see that the dip here in the fundamental, here at 200 Hertz, generates, of course, a very high peak here in the relative distortion metric. So that means we are getting a quite sophisticated response, but we know it's not the speaker, it's the room. So that's why we are using or generating again our room correction curve. We have spoken about that in the, oh, no, that's this one here. Here you see our room correction curve. If I apply that or calculate a new one based on that, but it should be almost identical, I end up with a new measurement where I get a very smooth curve. Here the room responses are, also the imports is much shorter. Maybe I switch over to the other measurement and compare that. Here you see it goes immediately down. Here we have some ringing, but we see it much more clearer here. Yeah, here it goes at -30, it goes down. That's more or less the room here. Yeah, and we end up with a much smoother curve, which you would measure in an anechoic room. No? Okay, and that means that also our relative curves, or absolute curves here, are much more meaningful noise. They are smoother, easier to interpret. So that means by measuring in an anechoic room or with this room compensation method, you can simplify your results from the THD. That's very, very important. Let's go back to now to our slides where I show that in greater detail. No.
Wolfgang, just a quick question.
Yeah.
What are the harmonics that are included in the THD?
They are here. Up to the order you're asking?
Yes.
How many? Okay. You see it immediately if I'm going to curve property. No, chart. No. Sorry. Here it is. Customize subset. And here you see what we have. Here we have some single up to the 18th order. You get them always, or almost always. Maybe I can activate them, then you see it. Or I activate all of them. Then you see there's a lot of noise-like signal here. Usually you don't need more than the 18th, but we have more. If you're making your sweep slow, then we are getting automatically more harmonics. Yeah, does it answer your question? So everything from that single or second, third up to the 8th order and sometimes more is summarized in the THD.
Very good. I suspect anything above a 3rd or 4th order is just being masked at any rate.
Yeah, it is masked, and there's a lot of noise here. Actually, I assume after the order of 10, we are already in the noise level. Here you see, below 0. So here we have something. With the 7th order, we get some meaningful data. And this is also close to the noise level. So actually, without noise, we are usually here in the 4th order. This is here, that might be generated by the speaker on that here. Correct?
Wonderful, thank you.
Okay, now let's jump back to our slides. Okay. Yeah, yes, we have applied here the Farina technique. Here you see it summarized. That's without compensation. This is with compensation. And even not only the harmonics becomes shorter, even the impulse responses from the harmonics become shorter, also not only the fundamental. Yeah, so it reduces the ringing from all components. That's important, also for the harmonics. Of course, this is quite important for the Farina technique. You see, for the fundamental, we have plenty of space and time to apply windowing, but here it becomes very short for windowing out each harmonic. So that's why applying a room correction function is very important for harmonic distortion measurement, especially if you are measuring quite fast. Yeah. Okay. Here you see the difference if the fundamental is wrong, if the harmonics are a little bit corrupted by the room responses. Here you see the black lines are always with room compensation, and then we end up with a meaningful curve. You have seen it already on the Bluetooth speaker, but without, you have sometimes very high distortion values, which make not much sense. Yeah. That's why you see already, if you like distortion in percent and you are dividing more or less the distortion or THD by the total signal or the fundamental, you are prone to this kind of problems. You should be aware of that. No. Okay, I did already the experiments, so that's why we can skip that. I was too fast. And now let's speak a little bit, what is the best chirp for end-of-line testing? Yeah, we have spoken about the linear chirp. I know I have deactivated the sound. We have spoken about the log chirp. No, I forgot to deactivate that, sorry. And here you see that was a logarithmic chirp. And this was a very simple equation, how to calculate what is the sufficient sweep speed to grab all the important information. That depends from the Q factor or the highest Q factor generated by your speaker. So that means the Q factor at the fundamental is usually below 1 or about 1, and maybe on headphones it is mechanical Q goes up to 3, 5, 7 or something like that. So it's reasonable. And here is starting frequency. But if you have some modal vibrations, some rocking modes, then they are very tricky because the Q factor might be 40. So you need a much slower sweep speed. So now comes in the stepped sign. So, sorry, I play it again that you hear it. It comes soon. Here we have multiple periods, usually a certain number, 5, 3, maybe 10, but the frequency becomes higher and the period length becomes shorter, so it becomes shorter at higher frequencies. That sounds. And here you see a very interesting result that each period here, it becomes shorter no, with the frequency and so on, but we can calculate the length which we need depending on the Q factor. And if we are following this equation coming from the mass, it's very similar to that actually. Then you see it makes a lot of sense using a stepped sine wave where we are faster at higher frequencies with our sweep speed or with our frequency setting. So that means this is a real advantage of the stepped sine. That would be the right sweep speed dictated by actually by the Q factor of the resonances in the speaker. No? Okay. The stepped sine has only one disadvantage. We have a discrete frequency setting. So we are switching the frequency. It's not continuous. We cannot apply the nice Farina technique and so on. And we are losing a lot of time. So it's not a fast measurement. But the frequency time mapping is correct. So we learn from that the chirp with the increasing sweep speed is much better than a logarithmic one. So that's actually the best thing we can do if we are changing the logarithmic sweep speed with time. So that's this red curve, but unfortunately, then we cannot apply Farina. With Farina, we need the constant sweep speed, at least in a certain frequency band. So the conclusion is quite simple. We are approximating the blue stepped sine curve with different sequences of logarithmic sweeps. And we are switching at that point the sweep speed. So we have more or less something like that. So we have here at lower frequencies, the low sweep speed, and then maybe 10 times. That's just what is correct. So we are here a little bit too fast, here a little bit too slow, but this is a good approximation. We are much better than with a logarithmic, with one logarithmic chirp. So that's the whole idea. Here you see it over time. Now in the last 10%, we are covering almost half of the audio band. Now, all that here from 200 Hertz up to 20 kilohertz. That's more or less right stimulus for end-of-line testing. Okay, shall we sweep up or down? Big question. To make it very simple, if you use a logarithmic chirp and you have plenty of times, that means more than 1 second, 2 seconds, it doesn't matter. But if you are doing ultra-fast testing, then it matters. Here, for instance, we are sweeping very fast, half a second. sweeping downwards, yeah, then you get more distortion here in red, 20 dB more. Sweeping upwards, you get less. What measurement is correct? If you are a customer, you are afraid that maybe the red one is correct. If you are a manufacturer, you would like to see the green one as the correct one. Actually, the green one is the correct. And what causes that? That's actually a fundamental resonance. Here, at about 1 kilohertz, you see it also here. That's here cumulative spectral decay pattern. And you see that this resonance is ringing forever. Ever means 200 milliseconds, 500 milliseconds. That depends on the Q factor again, what we already discussed. So if you have a high Q factor, you get a long ringing. And now happens a very bad thing. If you are sweeping downwards, here from that, you are activating with the fundamental, because the fundamental will be the first one, which is just at the resonance. Here you're activating the ringing goes on, the fundamental is already down, and now the second order harmonic will come at this frequency, and will be, this ringing from the fundamental will be interpreted as second order distortion. And then the third, fourth, fifth, and so on. And here you see that's why we get here a lot of information from that. So that means if you are measuring fast and at end of line or in your workshop, don't do that. Sweeping upwards, then always the harmonics are acausal. They are coming anyway too early. So, but not here, sweeping downwards. So that's the problem. No. Okay. More to this topic, if you are doing really fast testing, then please read this paper here. That's about particularities of end-of-line testing and the physical reasons. Why is the measurement speed so important and how to find the best condition. That's quite interesting. Yeah. Okay. Interpretation of the harmonic distortion. That's our main topic today. I'm good in time, so we are at the right point now. What is our objectives? Actually describing the properties of the distortion on a good metric. So on a right scale where it is quite easy to interpret the results. And understanding the relationship between the numbers, between the curves and the root cause. Yeah. And really evaluating the impact on the perceptual sound quality, all that. So we are exploiting the following properties. We are speaking about even and odd order. Second is even, third is odd, and so on. Then we are speaking a little bit about the THD, what is an energetic sum of distortion components, and then the frequency dependency of the harmonics and the amplitude dependency of the harmonics, and of course low order and higher order harmonics. Yeah, and then of course some interesting metrics, the energetic sum of different harmonic distortion components. I'm coming to that very soon. Let's start here with the even and odd order distortion. Here on the right sides, you see the total harmonic distortion relative. So that means we have summed up the distortion that's identical like here on the left side, but we have divided that by a reference quantity. Usually it is the total signal, but there are some other ways to use PREF. So the PREF might be the total signal. It might be also only the fundamental or the mean fundamental in a certain stated frequency range. Okay, then we usually come to the percentage value, but of course we can also describe that in dB. If we are using this THD metric, then we get on an absolute scale, then we get usually such a result. That's driven quite hard, so we have applied a high voltage. Then we see here the fundamental, and then we see here the absolute total harmonic distortion. The interesting point is that in the passband, the THD is usually far below the fundamental. Here 20 dB or 30 dB. Less here at a certain modal resonance, but at very low frequencies, usually the THD absolutely comes up because we have a lot of displacement. Here is a base signal, more or less active, and the fundamental goes down. So we have two reasons why we get actually, or why the harmonics are higher than the fundamental. Yeah, please keep in mind, this is the excitation frequency. That corresponds with the frequency of your generator. It's not the frequency of the second, third, fourth, fifth harmonics. They are at much higher frequencies. That's a little bit confusing. So that's our resonance frequency. And now come some interesting results. I can just present that here. You have to believe that. Later on, I give some comments to that, how this result comes up, but we don't have the time to going into the details. The stiffness from your suspension generates harmonics at very low frequencies, usually below the fundamental resonance frequencies. Why? We need displacement, and we only have this here in the base region. From the BL, it's almost the same result, but we see a little bit more at higher frequencies. That's because at higher frequencies, the BL distortions are decaying at a more shallow slope, not as steeply as the stiffness. Why? Because current is also involved. And now we see the inductance. With the inductance, there is a really bad news. We are very insensitive for this kind of nonlinearities or symptoms. Why? Because we have either not enough displacement at higher frequencies, or at lower frequencies, everything is attenuated by a differentiator. So you are blind for L from X, and that's pity. If you would like to check whether your shorting ring has improved the performance of your speaker, then the shorting ring, the copper ring, or the copper cap would improve the L from X symptoms, but you are almost blind for that with harmonics. L from I, here we need only the current dependency. That actually generates here the flat response over a wide frequency range. You are very sensitive with the THD for L from I. For cone vibration, we are here just at such a resonance. Yeah, that depends on the particular modal behavior of your speaker. So that's more or less a result. And that can be explained by this generalized signal flow chart. That's here the linear path. We have spoken about that. Here is more or less a linear behavior with the Thiele small parameters. That's a high pass characteristic from voltage to sound pressure. But here we get some distortion generated to the input. You have seen already in the last sessions the blue box. Now we are looking into the blue box. You see how the distortion are generated. We need usually two signals. Here in this case, they are generated by two filters that are here, for instance, for the current band stop filter, and here for the displacement is a low pass. So then we have two state signals, time signals. The displacement is fed here through the maybe nonlinear stiffness or inductance, and then it's multiplied with a multiplier. It's shaped here by a differentiator for the inductance and added to the input, and that's in a feedback loop. So that's the general model for generating the nonlinear distortion, and they are generated here in the static nonlinearity, in the nonlinear curve, and in the multiplier. This multiplication of two signals is just not allowed in the linear world. Okay, we have not much time to speak more about that. Here's those linear filters. They are shaping a little bit the signal. That's not dramatic. Yeah. And here you see the different nonlinearities. We have a couple of them in real loudspeakers. And here's a physical interpretation. If you download more or less a handout, then you can study that. Here's our, let's go to the inductance L from X, we are multiplying here. We have actually two effects. One is the self-induced voltage. We are multiplying current with displacement. We have a low-pass filter for the displacement, a bandstop filter for the current, and we need a differentiator as the post filter. That's more or less the case for the inductance L from X. Yeah, and everything is here different. Now the interesting point. The filter responses from the two filters, they generate the frequency dependency of your harmonic distortion measurement. That's why this table here is quite important for you to interpret or to explain the last slide where I say the BL is dominant at lower frequencies, something like that. We have not the time for going into this relationship and speaking more about that. If you are interested, please come to Drayson. Every year I have to submit here a lecture at the university. That's here in the March 19. That's usually about 100 people from the industry and from universities and something like that. So, and you find also some interesting information about this relationship between symptoms and distortion measurements. Maybe you have this already. Okay. Now let's do a simple interpretation of what we have measured. Okay, I'm jumping over to here to that, and now have a look to that. We go to the smooth curve here. That was exactly that. That are the higher harmonics. I dislike them. I make here reset properties. Then it looks a little bit more clean. And now look only to the THD. I make it a little bit larger that you see it. We have a maximum close to the resonance frequency. And if you remember right, that could come from stiffness and it could come from BL, yeah, and then it's decaying here. And if you look very careful, it's decaying more or less with 12 dB per octave. That's more or less. Let's go here to 300 Hertz to 600 Hertz. That's about 12 dB here from this point to that point. Yeah, and this is just like displacement. So we have one displacement, it goes down by 12 dB per octave, times current, which is in this frequency range almost constant. That comes from BL. Stiffness would go down by at least 24 dB for the second order distortion, and even steeper for third and so on. And that's what I said here for the BL. That's also only true for the second order distortion, but you see it's dominated the THD here by the second order distortion. That's from BL. And you will see it is caused by the asymmetry of the BL curve. We have a voice call offset in the speaker. That I can directly see from the harmonics. At higher frequencies, we here the third order are dominant. They are coming from other causes, maybe from modal vibrations or from the L from I. But we are 50 dB down or something like that, so it's negligible. Okay, that's an interesting interpretation here. That's possible if you are looking to the absolute presentation. It is not possible if you are looking too much to the percentage application. Why? You get here in percentage at lower frequencies a huge increase of the THD up to 100%. That's why, because your fundamental goes down. And maybe here the DSP processing has also reduced the fundamental. We have a high pass in it. So we are only getting here some noise and some other bad stuff. So that means all the high values you see here, they are maybe not true. Now this may be noise dominated. Yeah. Okay. Any questions to that? Kent, do we have some hot questions to the short?
Well, we've got some questions going back a little bit. And we can clean those up. For example, we can clean up one question. If KLIPPEL has physical measurements in an anechoic room to compare with their processing, and how well does the harmonic distortion match?
Of course, sometimes we have here in Drayson at the university an anechoic room, a big one, but it's very inconvenient for us to drive here for half an hour to the university. But of course, we have compared the anechoic measurements here with the near field measurement, and also here's a simulated far field, free field condition, and also with the near field measurement from the from the near field scanner. So we do it if you have some doubts. We have some new projects running where we are doing some nice acoustical near field measurement on transducers. And here we are doing again the verification that our measurements with the near field scanner are identical with the anechoic measurement.
Wonderful.
Of course.
Thank you.
Okay. Then I go on here with our measurements. Here comes the next poll. Now you should become active again. Do you prefer to present and to interpret the distortion on a relatively metric? A, no. Absolute component on the same level as the fundamental. Yes, you refer it to the fundamental amplitude response. What we have, no, we have done. You can do it only to the fundamental or to the total, also THD and fundamental. And the next, yes, that's in both cases, please indicate B. There's only usually a minor difference at low frequencies. Yeah. Okay, C is completely different. Here we are referring this only to one value. That's the mean value of the fundamental response. So that means here we have almost the same shape like from the case A, from the absolute components. The only thing it is referenced to the mean value. You get it also in percent. This is a very interesting alternative which combines the benefit from A and B. You get it in percent, but you avoid here the strange noise effect, noise problems and so on, or some other problems. Let's see. I'm happy to see that most of the people are working with the absolute components because it's actually much easier to interpret. Of course, I expected a lot are working with a normal percentage. C is not very popular yet, but it is supported by the IEC standard. You can use that. But you have only to explain what you are doing. That's referred to the mean value. That's a very good idea, by the way. Okay, let's go on. Harmonic distortion, relative or absolute. Here you see it. The problem is you get high values here if you are referring that to the total signal. Here the absolute is much better. If you're doing that in the far field, in a really room, you get crazy results. Why? Because the fundamental is so complicated, and even the harmonics are complicated. By dividing them and getting a percentage value, you get only crazy numbers, 40 dB of variation. It makes not much sense. Yeah. So that means if you are using relative values, you are dividing that by the total output. Yeah. Then you have only one benefit. It's in percentage, and it can be interpreted actually for a single tone. It can a little bit explain the audibility of the harmonics, but only for a single tone for this particular thing, but not for music. The disadvantage is the linear response will affect your metric. You get a high complexity. Each harmonic is scaled in a different way because that's a post-shaping when the signal goes through your speaker. So it becomes very complex. The interpretation is difficult. And it is not, even that here is not 100% precise psychoacoustical processing of the masking. That's not true. So it's only very rough to compare that. So if you would like to use the percentage value, you should So first of all, we recommend to interpret this on the absolute scale. You can work with the equivalent harmonic input distortion, are coming to that, or you are referring to that to the mean value. And if you are really interested here in the audibility, then you have to use a perceptual modeling to explain what happens with your harmonic distortion measurement. Okay. Now we are on the equivalent harmonic distortion measurement. That's actually a new thing provided by the standard, and it's very powerful. Up to now, we have used a microphone to measure here in the sound field, the output. We have used Farina techniques or any other FT to separate the fundamental from the harmonics, and we get on each observation point a different response. This is more or less caused because here the linear transfer function are different. So that means each point is affected by the room response, and maybe the loudspeaker has a different directivity pattern. So, but most of the nonlinearities, the dominant ones, they are actually concentrated in one nonlinear block, adding nonlinear distortion to the input. So they are only different shaped, not more. That generates a different curves here from the absolute harmonic distortion components. By the way, if you are dividing that here to the different fundamentals, it becomes even more complex. Now, what is the idea? Removing this shaping. That's more or less what we also have done here, removing the room influence with a simulated free field condition. But now we are taking the complete linear response, including the tele-small parameters and normal behavior of the loudspeaker. So effectively here you see the -1 in the exponent. This is canceling out. We are effectively at this point here, at this point, as close to the input after the distortion are added. And now the interesting point, those signals here, they should be identical if this is true. And if I do that, here in this example, you see over a wide frequency range, I get the same curves, flat, smooth curves without ripples. So it's much simpler what is behind the whole system. All the nonlinear distortion are generated here by the red block. Here at higher frequencies, we are in the noise, and then it becomes more complicated. So be aware of the noise. The noise is the only enemy for this kind of business. So it's a very interesting thing to simplify your curves and to get the same information. And it's more meaningful. Why? Because 0 dB means the full voltage here. Here, we are effectively at this point. That's more or less your generator voltage provided by the generator. And that are the distortions here, D from T, added to the generator signal, minus 25 dB. And all that is independent on the radiation, independent on the position, independent on the sensor. You could use a laser sensor, a microphone, an expensive microphone, an inexpensive microphone. If the microphone generates no harmonics, and usually it is not the case if you are far away and the sound pressure is low, then you get always the same curves. Quite nice. Yeah, but what happens if this is not true, that the nonlinearities are actually are added to the input? Here you see a second nonlinearity adding. It's a little bit more outside. It's more or less at the surround or on the diaphragm, but not at the voice coil. It has nothing to do with the BL, with the stiffness. Of course, then we get a different distortion signal. Here you see those distortions here are not affected by any further nonlinearities. They are shaped by this linear system, but here are some additional distortions are added. And then we see at higher frequencies usually a disagreement. And then you know, here's the second nonlinearity in the multi-dimensional signal path. That's a one-dimensional signal path, and that's depending on the position R1 and R2. Okay, here an example. Here you see I measured at near field 10 centimeters, 50 centimeters, 1 meter. Over a wide frequency range, it's identical. Only here where we get some modal vibrations from the surround, we have different distortion depending on the position. Why? Because we are radiating the distortion directly from the surround to the point. Yeah, and those here are generated at the input. They are generated here somewhere else. That depends on the position. And now another consequence, the equivalent harmonic distortion are actually measured here at the input. They are more or less what is generated from the dominant nonlinearities, BL, inductance, and so on. And they can be canceled in a DSP by a nonlinear processing, signal processing. So we have to synthesize the same equivalent input distortion, but instead of adding them, we are subtracting them from the input. And this signal cancels that. We have a linear input, the distortions are gone, and we get only the linear shaping from the linear system. So that means only the equivalent input distortion can be compensated by the DSP. And we are, with the nonlinear business of canceling distortion, we have better chances than with the equalization. With the equalization, usually we get a different response for different points, so we are very much limited. But the BL distortion, inductance distortion, and even sidefire distortion can be canceled by DSP processing. So that's quite important. What are the benefits? We describe the dominant distortion, or we transform the distortion to the point where they are generated, and we are 100% independent on the transducer, on the linear part, yeah, on the room, on the distance, on the sensor. I said this. It works quite nicely here in a normal room, in an office, even in a QC test box. Of course, in an anechoic room, the curves become even more simple. They are smooth curves, and you can quite interesting, describes them as a percentage of the input voltage, if you like. Yeah. And they can be cancelled by DSP. What is the only problem that is ensures sufficient signal to noise? Why? By doing the inverse filtering, you are maybe boosting high frequency signals, also noise up, and you may interpret them as harmonics. But if you are doing that in the near field measurement, then you are 100% safe. Yeah, I would like to make a demo. I'm using here the transfer function. Let's do that. I'm jumping to that. Any questions to the slides, Kent?
Yeah, I think we've got a couple that relate immediately. One of them is, how do you measure THD over temperature?
Temperature.
Yeah, what? Temperature is involved. Heating, I suppose heating and cooling.
I say it very simple. It makes not so much sense. Why? Because you can make it much simpler. If you know your compression, and you know it's thermal compression, then you know it is related to your resistance. And if your resistance is increased due to the heat, then you know your displacement goes down, or your impedance goes up and your current becomes smaller. So you can much easier interpret this in the variation of displacement and current. So I have never done a measurement versus temperature, but it makes a lot of sense to immediately study that as a change of displacement and current due to heat.
Interesting.
Yeah, okay. Another
yeah.
question?
What is the procedure to measure EID?
It comes soon.
Okay, good.
That's the demo. That's a good question. Then I take it and I do it. If we are going here to the, seal that. And now actually I'm doing a very simple thing. I'm doing a normal measurement in situ without compensation filter. I have to show it. Normally, oh, I have to go back. I forgot to say it. In the in situ compensation, I'm using here a pre-filter just after the microphone signal. You can deactivate that. If I'm doing that, oh, I have to go back so that you see the right slide. That's now deactivated. You see it's quite rough. If I'm activating that, then it becomes, we get our nice smooth curve with a room compensation curve. Yeah. And if you look to that, here is a curve. Here are the amplitude and phase response coming from the in situ. Okay. Now I'm using the same feature. I remove here everything. I'm jumping to the equivalent input distortion, and we have not activated up to now the reference filter. So I'm doing in a normal way the measurement. Now at 30 centimeters, I have to switch on my Bluetooth device again. Okay. So, okay, this is a normal measurement. It looks quite bad as we have measured it before. Yeah, it's the same. But now I'm I get the magnitude response. If I only grab that, I only get the amplitude response. If I go to the export, I can export here actually the transfer function, also the amplitude response plus minimal phase. I do that. Now the data are here in the clipboard. No. Why minimal phase data? I would like to get rid of the time delay problems, so that are synthesized phases based on the amplitude response. But this is quite important. Why? If I'm using that now here under processing as a pre-filter, I'm importing that here from the clipboard. Then you see I'm virtually now at the input. Here you see my magnitude response is almost flat here. It's only half a dB. Here this is noise. That's from my laundry machine downstairs. And here we have variation from 200 Hertz. That's less than 1 dB, half a dB. So we are actually now here with the fundamental response at the input. Yeah, but minus 18 dB because that, or 12 dB or something like that, that corresponds just to the voltage of 170 millivolt. Yeah, so 0 dB would be just 1 volt. So we are with the fundamental a little bit down. And now we have here our equivalent input distortion. If I remove this filter, then you are again at the output. Here you see it. And if I activate that, this is here the nominator, that's more or less the microphone signal divided by the stimulus, divided by the transfer function, that's the inverse filter. So we are canceling out the room and the transducer. We are effectively at the input, at the terminals. Now everything is flat, and here you see your equivalent input distortion. So that means we are 20 dB down. It's a very nice flat curve that comes from the speaker. Here the third order has a significant dip. This is unusual for a sealed box enclosure. It's not a sealed one. Here is a passive radiator and the passive radiator is generating more or less this dip here and something like that. I know it from the harmonic distortion. I have not looked into the speaker, but that makes sense. But you see, quite simple, very easy, without, here measured at 30 centimeter distance in situ. Okay. Yeah, now let's do the same measurement, or I've done it already. Maybe here you see it for 2 centimeters. I could move only to show it, the microphone here close to that. If I'm doing the measurement here, I get the similar curve, but much more flat. Why? Because we have a better signal to noise ratio. Yeah. Okay, and then I did, that was a little bit right. We saved the time. And then I did another measurement, a little bit left. So if I click on that, here you see the curves are almost identical, but there are minor differences. For you, I have placed all the curves in one chart, and I make it large. Here you see the distance of 30 centimeters for a little bit more noisy, but at 2 centimeters we get quite nice curves. But look to higher frequencies. Here we see different equivalent input distortion. This is here 100% generated at the input by the same transducer. Here we have different distortion in the surround from the modal vibrations. No? So that means here at 30 centimeters, it's more or less canceled out. But on the left and right side, we see some different modes. And the same here at higher frequencies. And the passive radiator has also changed here something at lower frequencies. No? Here you see there's a big difference here, almost doubling the distortion from the passive radiator. You see, it's much easier with the equivalent input distortion to interpret the data. That's your message. Yeah. If you are doing the same with the normal relative distortion in percent, no chance. You get any value you like here in 1 meter because you are actually the following fundamental and the room influence makes everything very strange. You cannot interpret that. In other words, you should try, if you are doing harmonic distortion measurements, to get relatively simple curves. Then you are doing good harmonic distortion measurements. And what means that? Measure in the near field. There's not a big need going into the far field. It's only post-shaping. And move a little bit the microphone around that, and then you will see usually quite nice flat curves, a little bit different, telling you something about the modal vibration and other things. Okay, any questions to that? That's a very, very important point here, and maybe we should really allow some questions.
There aren't any questions specifically to EID.
Okay, then we use the time.
Right.
Go on. Oh, okay, let's go on. Next poll. Do you use the second and third order distortion component for loudspeaker diagnostics? Also that's the separation between second and third. 100%. That's what, no, not. I was too quick. I
spoke too soon.
Yeah. See, here's a 12% of people who are not working with the second and third. It's a good idea to look to the second and third because they are telling you something about the transducer. And that comes very soon. So let's speak about some shape of the nonlinearity. We are speaking only about the static nonlinearity. So that means the linear systems are not important. It's just here the BL curve or the stiffness curve. They have no memory. That means static, no frequency dependency. It's like a diode or something like that. And we have a symmetrical nonlinearity. If we have a symmetrical shape, we end up with the fundamental and third order harmonics and fifth order and higher order. And the interesting point, by the way, is that we see usually in speakers it's the same distance between third, fifth, and so on, usually, not always. So we get like a Christmas tree, something like that. And the same for the intermodulation distortion. Okay, now an asymmetry. Think about you have here a very, very bad BL curve. You have a huge voice call offset, and you have such a straight line in the BL curve. Then you get actually second order distortion. And you see also force over if you have an amplifier as a cause of the nonlinearity. The amplifier is limiting on one side maybe. Then you see second and fourth. In a loudspeaker, but no third, yeah, or not much odd order distortion. But the loudspeaker you have seen it has a feedback loop. Oh, no, I have to make it in the right way, something like that here. Here you see it. Due to the feedback loop, we are feeding back the second order distortion generated by the asymmetry to the input. It is multiplied again with the input, and then we get third. And then it's again feedback to the input. We get fourth, then we get fifth. So we get everything, even for an asymmetrical nonlinearity. That's very important for transducers. Sometimes you read in some books, you get only second order distortions, only even order distortions from asymmetrical nonlinearities. That's not true. You get also third and fifth. Okay, but that's quite simple, and you should consider that. Next poll. Do you evaluate higher order distortion components? The first question is, what means that? We are defining that very soon. Much higher than third and fourth and fifth. Maybe usually starting with 6, 7, 8, 10s and something like that. No. Yes, only fourth and fifths. Yes, you are summing up the energetic sum of higher order distortion starting somewhere here. Usually you can modify that. D, yes, I'm using the weighted higher order distortion that's introduced by David Clark. It's also called Blatt distortion. Or you have some other ideas. Here I see the result. The majority say no. Why? Because everything becomes now a little bit more complicated. And it is really complicated. And the main enemy, again, is noise. The higher order harmonics are usually very noisy. If you are working with them, you have to really do a near field measurement like here to put the microphone very close to the speaker. Yeah, fourth and fifth. There, I'm usually looking sometimes to that if I expect a very hard limiting. The energetic sum of the higher order distortions, they are too noisy for my taste. If I really check the noise content, I find usually a lot of noise in that. So this is also quite interesting from David Clark. I'm coming back to that very soon. But first, let's start with the soft limiting. We have here more or less a loudspeaker which starts already at in blue here with at very small displacement with some nonlinearities. Yeah, and due to the feedback loop, you get an early but very soft limiting. Here in red you have an overhang coil. Which has a very nice linear behavior over up to 4 millimeters. The coil sees more or less the same BL. It's beautiful. But then some windings go out of the gap and you get a very sharp decay. And here you see what happens. We see a very narrow, say, Christmas tree here from the intermodulation distortion and from the harmonics. So we have dominant second and third, mainly here third because it's so symmetrical. The even orders are much smaller, either third, fifth, seven. But if we have a hard limiting, you see that our Christmas tree is much wider. You are generating almost the same third, fifth, sevens, nines, 12s, and so on. What means that? If you are operating this beautiful, very expensive loudspeaker to the point, to 5 millimeters, where half of the windings are out of the gap, you have much more higher order harmonics than for the inexpensive equal length configuration, which is much cheaper. So that means if you have a plateau, you should only operate this up to 3 millimeters. That's one consequence, practically speaking. So we get a lot of more of higher order distortions. So here you see the definition from the IEC standard. We are summing up the higher order harmonics based on an energetic measure, the squared, starting at a user-defined order, NL, usually 10 or 6 or something like that, and referring it again to the total signal or to the mean value or something like that. Yeah. That's one thing. That's maybe a candidate for rub and bus measurement, but it's a very, very poor metric. Why? Because you are prone to noise problems. There's a much better way for doing that. The weighted harmonic Platt distortion only goes to the 10th order. It starts with a second, but it uses a very special weighting function introduced by David Clark. And that's, here you see how it is defined. It's a little bit more complicated, but this is a very nice way to evaluate the strange sound generated by a suspension which is limiting. That happens in some automotive speakers if you are using the suspension as a protection system. That's why they are calling that here Platt distortion. Yeah, and yeah, it is not good for rub and bus, but it's very good for evaluating this kind of sound, which sounds a little bit aggressive or sometimes unpleasant. Yeah, what is important for that? Ensure sufficient signal to noise ratio, makes a measurement in the near field. That's important. Now our next poll, do you measure the harmonic distortion at different input voltages to investigate the amplitude compression? Please give me your poll. Yes. 90% will say yes and only 10% no. I say you should measure at different voltages. Why? If you change your voltage, you get maybe less distortion. Even at higher voltages, that might happen. So that means your result depends very much from the level of your voltage of your stimulus, from the input amplitude. You will see. Here you see third order distortions. I have increased the voltages and I have plotted here the distortions. That's here on a relative metric. You know, it's not so nice to look to that. So that means it's referred to the total signal. We get the natural compression effect. We are never higher than 100%. So we are squeezing all those higher voltages here in a natural way together. But for higher voltages, more distortion. That's true for third order, usually. But what about second order? Second order, usually you get a very fancy behavior that at certain frequencies, you really see that the distortions are rising with amplitudes, but there are some other frequencies where you get less distortion. How can this happen? Very simple. The loudspeaker generates with the second order distortion, especially if you have a lot of them, a DC component, and that shifts the voice coil to a certain position. And depending on the excitation frequency, you will increase the distortion with the DC. So the coil is moved out of the gap, or you are centering the coil quite nicely automatically, then you get less distortion. So if your customer is very keen here in this frequency range, and you can convince him to say, please provide a higher voltage to the loudspeaker, you get a better speaker, then of course that is quite interesting. So you are using the self-centering feature of the natural loudspeaker. But here it becomes unstable. Here you get more distortion, that's bad. So measure at different voltages, you get interesting results. Okay. We have here different tools for doing that. Now, let's come back to our examples. If we are measuring our THD, for instance, over voltage or displacement here plotted versus displacement that corresponds to the voltage. Why? Because you can compare it here with the BL curve. Then you see with the red speaker, the overhang coil with a nice linear plateau, we are staying up to 2 millimeters here in the plateau region, almost no distortion. And then we are here at the slope, we have a very, very high increase of the distortion. And if we are driving this to 5 millimeters, we have almost the same for the inexpensive equal length speaker or coil and for the expensive overhang coil. Yeah. Here the equal length has the benefit to have a very smooth increase. We have only second and third order distortion. Yeah. But here is steep but late decay. Okay, now let's do some measurements with different voltages. For that, we can use the 3D distortion. The disk is actually dedicated for changing the voltage, but I would like to show a new module which is under development. That's a voltage stepping. I used this already for the compression effect last time, and I would to use that also now here in our measurement. I'm closing that, and let's go first to the, or maybe I have here a work version. Here is my first TRF, which I only use for setting up this, the starting frequency, the end frequency, the voltages, and so on, and the windows, and so on. And then we have here our stepping module, where I can control more or less here the stepping. That's my starting voltage, that's my final voltage. Here is step size, and here I can select operation. Maybe I can show it. I press this, and then I see here this other measurement where I did the setting of the TRF. I select that, and now I'm copying automatically all the data from this template function into the stepping and doing the processing. So, okay, I can start that. And now we are, it's only for illustrating that. It should be actually here. I stop this very soon. Oh, it's dead. Here you see its noise. So the measurements stopped again. And we generated already one result function, but it's stupid because it's just noise. Here you see the result from a good one. I close that. I have done the measurement. And here you see the first measurement at 100 millivolt, then at 150, 200 millivolts, and finally to 400 millivolts, and so on. Yeah, and here nicely to summarize the results. We are now here in situ at 30 centimeters without room correction. We get all the strange results, yeah, from the room modes. So it's difficult to interpret. We have sometimes also the feeling here one measurement is higher than the next one here. Maybe it's very complicated. Now the same measurements with this simulated free field condition here in our transfer function. I clean up here the screen. Here is my room correction curve in it. I show it only here processing. The reference filter is activated, and here is actually the room correction curve. And it's actually the same like the equivalent input distortion, but I got this curve actually from the in situ measurement. So, okay, and now I have, here you see the result. I get the expected behavior. It's much smoother. The room is suppressed. We are now below 10%. If I'm comparing that with the other one, then you see the difference. This is with the room correction curve. That's without. No? Okay, and now comes the equivalent input distortion. I clean up everything, and I'm here. Here's the result, and here you see the results. That's a normal total measured actually at 30 centimeter distance at this position here. That's again the same picture as before without room correction, and that are the equivalent input distortion. About at the maximum 10%, nicely rising with the amplitude quite regular. Yeah? And what is interesting, that the maximum equivalent input distortion, they are now constant over a wide amplitude range from 200 millivolts to 400 millivolts. It's constant. We know there's a compressor in it, reducing more or less our fundamental. So we are not generating more distortion. Here you see the compression. The compression was about 4 dB. No? So that's more or less what the compressor is doing. Yeah, now I have changed here the position to 2 centimeters. Here's the result. It's almost the same result, but it's much smoother. Yeah, but the same curve shape. Here's the dip from the passive radiator. That's more or less the result. No, from both, from the loudspeaker and from the passive radiator. Okay, here you see the data. What means that? We get all the interesting data in the near field in a very fast and elegant way. We even need no room correction curves for interpreting the harmonic distortion in the right way. That's one of the big conclusions. Do you have any questions to the stepping?
Just looking through the questions here, there might be a couple. There's some general questions that we'll get to.
Yes.
Thanks everybody for hanging in there. But in particular to this, what options do we have to generate the in situ curve as shown during the TRF stepping demo?
More or less, I have copied, to make it clear, I used already here in section 4, yeah, I generated here, here's the in situ, that's more or less what we have done at the beginning. That's here the in situ compensation function, and this function here only the magnitude, not the phase, is more or less copied here into this transfer function. That's it here under processing.
Right, very interesting. Is there any benefit from using the KLIPPEL processing while also measuring in an anechoic room?
If you have
frequency, maybe.
I have spoken about this already at the previous sessions. If you have a poor anechoic room, what makes a lot of sense,
right,
so not so expensive, then you can apply the room correction function at very low frequencies.
Right, makes sense.
At higher frequencies, we have our windowing and so on.
Absolutely. I think we can move along.
Okay, then I'm almost at the end. I'm happy that you stayed with me. Let's go on. Yeah, that was a general discussion. Do we have some other questions?
We do, and these, I think, come during the course of the conversation. So some of them are metric related. For example, does Qmax mean the maximum between the electrical Q and mechanical Q?
Actually, that's quite interesting. The mechanical Q, the high Q values are dangerous, yeah, because it's ringing very long, and that then to get steady state condition, you have to wait for a while, and you get the high Q values usually from the mechanical Q, yeah, and so that means if you are speaking only about the fundamental resonance, this is not a big deal. Why? Because usually the electrical Q is dominating and damping also, or providing enough damping also for the mechanical things. But the main problem are the modal vibrations, the rocking modes, which have usually a Q factor of 20, 30, 40, or some other modal vibrations from the surround mode and so on, which have usually a Q factor of 10 and higher. And they are critical. If you are working with headphones, for instance, then sometimes you have very narrow, very bad resonances, and they may generate some rub and bass. And to get the rub and bass, then you have to consider with the sweep speed more or less those resonances.
Interesting. Tying into that, what are usually the cause of subharmonics, and when can we expect them? Can they be identified by a THD measurement?
No, from the definition, harmonics are at higher frequencies and subharmonics are at lower frequencies. We have some tricks to use the DIS, but you should be not afraid from subharmonics. They are usually quite hard to measure, but here is how they are generated. Think about, you have a mechanical system, something like that, and you're pressing it down, then this ruler goes to the left and to the right side. Yeah, that might be that's one mechanism to generate subharmonics. They are usually related to other nonlinearities and so on. They are critical if they are falling in another different resonance and something like that.
Right. I think we'd attribute those to surround, potentially.
No, they are usually in the cone. They are less in the surround.
Interesting.
The point is, if you hear bad sound, then you should, or let's put it, they are not directly harmonics. They are subharmonics, I know, but in no standards they are considered. That's why you will not find them with, or you cannot measure them usually with harmonic distortion measurements. They need a different metric, but they are not really so important. And they are more related to rub and bass. So that means we should come back to the subharmonics, and I do, to use similar tools for the rub and bass measurements. They can also be applied for the subharmonics.
Very interesting. There's one little cleanup question. A comment was, again, going back to the anechoic measurements, and if the processing works on distortion measurements in comparison between a true anechoic measurement and the KLIPPEL processing. Yeah, if essentially the distortion measurements measured in an anechoic chamber match well to those of the KLIPPEL compensation.
Absolutely, we checked that here with the examples. Yeah.
Right, that's kind of what I thought. Okay, that's it for questions. Boy, we've gone about 100 minutes. Thanks everybody
No, I have the
for hanging out with us. I was just going to hand it over to you for the summary. I think we've got this practiced. I know that you're going for the summary right now.
Okay. Also, let's summarize this. Harmonic distortion measurement reveals useful symptoms for system nonlinearities. But I met so many people who are frustrated with the interpretation of the harmonic distortion results if you are using relative metrics and you are measuring with noise or with room influence and so on. Your target should be to get smooth, simple curves. It's possible, and they are meaningful. That's the point. You can do with a chirp, quite ultra-fast measurements. Yeah, that's quite interesting. And you should think about increasing the sweep speed at higher frequencies. The equivalent input harmonic distortion simplifies the interpretation again. So then it becomes very easy. It's directly related to the signal flow chart I presented, so it's quite simple. And in the future, the equivalent input harmonic distortion will become even more important, because then it's just the important thing for the DSP guy who are using the DSP for canceling that. So you can speak with the transducer guy. I have to synthesize 20% of harmonic distortion at 100 hertz or 2 kilohertz in a micro speaker or something like that. And this is a lot compared to the total voltage. You have to improve your speaker. So it's quite nice to express the harmonic distortion in volt of the stimulus. So it's very important. Yeah, you should change the voltage always to see how the different shape of the nonlinearity will affect your measurement. So that's quite important. Yeah, and harmonic distortion, measure it in the near field. That's really a good idea. So that's maybe everything. Yeah, we have, of course, some open question for the next time. Harmonic distortion is only one symptom. It's easy to measure. It's very convenient. It is useful, but it's not everything. The next time we are, oh, here's something misspelled. We are speaking about the intermodulation distortion. We are studying, or I tell you about what the 291 is providing for that, and such questions. Why are the intermodulation distortion usually larger than the THD? Even in the passband, in the audio band, even for the speaker. The speaker here is very nice made, but I told you he has a voice call offset. But you have seen that the THD was less than 1% at 1 kilohertz. You will see that this loudspeaker generates about 12% intermodulation percent, 12% at higher frequencies. And that comes from the voice call offset. Yeah, why is the amplitude modulation distortion more critical than the phase modulation? How to simplify the intermodulation measurement? We are speaking about the multitone testing and how to interpret the result. So that's the next time. Next week, then we have another one in 2 weeks about the impulsive distortion measurement. And then I will make a small break. I will start again on July 2nd, 22nd, because I'm doing some vacation after Corona, canoeing, and so I'm not here. If you would like to plan that. But we are putting, anyway, we are going on, also we have the next 2 weeks regular webinars, and then in July.
I think we can all appreciate that. You put your work in today, Wolfgang.
Yeah, I thank you very much for your attention and for staying with us. I hope it was useful for you.
Wonderful. Thanks. I agree with that. Thanks, Wolfgang. Thanks for everybody showing up. Remember to stay safe as we open up. Love what you do and love those around you, and we will see you soon. Thanks, everybody.
I will fix the small problems I detected in the... Ach yeah, it's interesting. Also, I fix the problems in the handout or maybe in the movie, the errors which I found. And another advertisement is the Alti. Next Monday, I will present 2 papers. One is about transducer modules, using here the KLIPPEL control sound, here the active compensation of distortion and other DSP processing in active transducer modules. That's one interesting point. And the other thing is a short summary from the end user value I presented here at the EAS, a 90-minute tutorial. At the Alti comes only a 25-minute short version of that. So
right.
Next Monday, I hope to see you there.
Right, and for those of you who are hanging out, there's a link to that presentation, or at least a link to what's happening in your chat window. I'll also remind you that you can always go back and review any of these webinars on the registration page. If you scroll down, you'll find movies, and I will have session 7 and posted tonight, and then we'll have this session posted as soon as KLIPPEL gets that to me. Okay, that's it. Thanks, everybody. Stay safe, and we'll talk to you soon.
Bye-bye.